Okay, kids, it's physics. So you know there's an equation for everything. We just went over the electric field lines and out of the positive and into the negative thing. That's what a test charge would do, placed in that field, blah, 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 showing the different strength by different amounts of lines. Okay, all that. That's all conceptual stuff about field. But we know physics always has an equation. We love equations, don't we? Yeah. Of course we do. Of course you do. Here's the equation for the electric field. The electric field equation is force per unit of charge. Force per unit of charge. How much force is there on a charged particle? How much force per coulomb? Newtons per coulomb. So if we take a charged particle and plop it into an electric field, how much force is being generated by that field on that charged particle? How many newtons per coulomb? All right, example. Let's say that we have an electric field and it produces 20 newtons on a 2 coulomb charge. So the electric field strength would be 20 newtons per 2 coulomb. I got a calculator? Anybody? Do you get it? You get it? Okay, thank you. What? 10? 10. That would be 10 newtons per coulomb of electric field strength. Now, let's say that we have another electric field and we take this 2 coulomb particle and we plop it in there and it's experiencing 10 newtons. So that would be 5 newtons per coulomb. Now we can make an assessment very quickly over, if we, in these two fields, which field has a stronger which electric field stronger? Get that out. Which electric field has a stronger field? So this is 10 newtons per coulomb versus 5 newtons per coulomb. Actually with gravity we never talk about this. We never talk about the field strength of gravity like this. We do in a way when we say the gravitational acceleration around the Earth is 9.8 meters per second squared near the surface. And the farther away we go, that decreases. So in a way, maybe it goes down to 8 when you're way out there. In meters per second squared. And so now we're talking about the strength of the field getting smaller and smaller as we get farther and farther away. But when it comes to electrical fields, it's very important. It's much more, we're going to see we'll be solving problems with electric field. And so it's much more important to understand that the electric field strength, okay, at a particular distance from a charged particle will give you a particular field strength to it. Okay, well, first of all, let me just kind of go back into this equation up here. Okay, look at that equation right there, that bad Larry. And let's make a substitution in. Oh, physics, you always do that with physics. You make a substitution in, you come up with a new equation. Exactly, check it out. So this is electrostatic force. So if we take our Coulomb's law equation, and we plug that in, this is going to be equal to K, Q1, Q2, over R squared, okay, divided by Q. So I just made a substitution. I put Coulomb's law in there. Then check it out. Look, there's a Q here and a Q up here. And if I multiply by the reciprocal, I can see that Q is going to cancel out with one of these Q's. Which one? I'm so excited. Because, in Coulomb's law, we have the amount of force between two charged things. So we got a thing and we got a thing, and there's an attraction or a repulsion between them. But now one of those is going to cancel. One of those Q's is going bye-bye. So let's say that we've got this charged particle here, and it's producing, it's just a positive 2 coulomb. So I'll draw some field lines around it. Oh, wait. What's wrong with that picture? Hello. Out of the positive. I made it a positive, not a negative. Out of the positive into the negative. So here we go. We got some field lines. Okay, out of the positive into the negative. And you take this particle and plop it in here. And, maybe it's a positive little particle. Little particle. This is that, and this is that. This cancels out with that. In other words, the field that's generated, let's go back to you. You are insignificant, okay? You are insignificant. If we take you and put you somewhere above the Earth, okay, your mass doesn't matter. What matters is the field strength of the Earth. That's what matters. The big guy, the big kahuna. So it's the big thing that's producing the massive field that matters, and not you, little Jew in the field. You don't get erased, get gone. Bye. Does that make you feel good and important? I'm here for you. Okay, so this is that. So the only thing that matters with field is the big guy. Okay, this bad layer right here. So we're talking about the field generated by this thing, not the little test thing that we put in there to see what happens to it. Oh, what would happen to it, by the way? You would go away because, test particles. No, taken off. Yeah, so this is another way to express the field equation. Yeah, this way here. Sometimes this works. Sometimes it's you have a problem to solve, and this is the one I can use directly. Other times I have to use this. I have to use that one. It depends on the problem that you're solving. If you're given a force within the field, then you can go ahead and use this. If you're not given a force within the field, you're given the charge of the thing generating the field, then we got to use that one. Okay? Sometimes one comes in handy dandy notebook, and sometimes the other one does. But those are our two field equations. All right? Two field equations. Physics always has equations. We love equations. Woohoo!